Hey guys, this is Mr. Beckstrom, and today I just wanted to do a little bit of a quick quiz 2 review just to kind of give you an idea of the kind of questions that are going to be on here. You're going to see mostly problems from section 3.3 and 3.4. These are going to be um, the product and the quotient rule problem. So you're going to make sure that you have these formulas out, that you've done quite a few of these examples, that you're comfortable doing them, that you can go ahead and convert between different algebraic expressions. And I'll show you a couple of examples here. So I'm going to do 3 examples, and we'll kind of go through those, and I'll show you a couple of techniques that I have to help me solve these. So the first one here I have is I want to find the derivative of 3x squared times the quantity of 4x cubed plus 4. Now I have two different ways that I can immediately see to do this. I can either use the product rule, since it's the product of two separate functions. I have one function 3x squared, and I can also identify a second function as 4x cubed plus 4. Or I could distribute this out into like one polynomial function and then just simply use the power rule. I think distributing that out using the polynomial rule would be the easier way to do it, but in this case, just for fun, I'm going to use the product rule, but you can use either one you want. So the product rule says, and I'm going to use the shorthand method of it, is that I take the first function times the derivative of the second function, and I add it to the second function times the derivative of the first function. And sometimes you also see that like g of x times the derivative of h of x plus h of x times the derivative of g of x. But for product, I like using first, second, and first. And for the quotient, I like using top, bottom, bottom, and top. All right, so here let's go ahead and identify everything. So my first function is equal to 3x squared, and the derivative of my first function is equal to, and just applying the power rule, you bring the 2 out front, 2 times 3 is 6, that's just going to be 6x. For my second function, I have 4x cubed plus 4, and my derivative of my second function, just apply the power rule, 3 goes out front, so 3 times 4 is 12, 12, reduce the exponent by 1, 12x squared, and remember constants go away. So here's all the information I need in order to put into my derivative formula. So it's the first function, 3x squared, times the derivative of my second function. So that would be times 12x squared, 12x squared plus my second function for, let me go ahead and so I leave enough space for my my second problem here. So plus my second function, 4x cubed plus 4 times the derivative of my first function, which is 6x. Alright, bunch of baloogadabee mess. Alright, so now just let's distribute that out. So 3 times 12 is 36, so this is going to be equal to 36, and that would be x to the fourth, x to the fourth. And then over here, I'm going to have 6 times 4 is 24, so that would be plus 24 x cubed, and x is x to the fourth, x to the fourth. And then we distribute that, so that would be plus 24x, plus 24x. And that up a little bit there. And so we can combine those two like terms there. So I should get 36, 46, 56, 60, 60, oops, didn't like that, 60 x to the fourth plus 24 x. And I would leave it just like that. So would it have been a little bit easier had we distributed that and done it that way? Yeah, I think it would have been. I mean, let's go ahead and do it that way as well. See how much easier it would have been. So if I would have distributed this first, 3 times 4 is 12. So that would have been 12 x squared, and x cubed is x to the fifth. X to the fifth plus, and that would have been 12x squared. 12x squared after we distributed this, and then you just apply the power rule, bring the 5 out front, and then that would have been 60x to the fourth plus, bring that out front, 24x. And you see we get the same answer a whole lot quicker. So there is a good point into seeing better ways to do some of these problems. Definitely seeing better ways to do some of these problems. Can you always do that with the power rule? Absolutely not, especially when you're dealing with different types of functions. Like if you have one trig function and one e function, you definitely can't do something like that. But if you have two of the same types of functions, like two polynomials, or if you have, you know, two e functions, sometimes even two trig functions, you can many times combine them like that. All right, the second one here, -5 e to the negative x. Now, when I see that, I immediately think chain rule. However, we don't look at chain rule until I believe section 3.7, so we have to look at something else. So we have to say, oh, what do we do? Because we know how to find the derivative of e to the x, but we don't know how to find the derivative of e to the negative x yet. We will soon, but not yet. So what do we do? All right, well, what we do is we do know, I'll do this off to the side here, we do know that if I have, let's say, 5 to the negative 3, that is equal to 1 over 5 to the positive 3. Okay. That we can move the base to the other side of the quotient line and change the exponent from negative to positive or vice versa. Hopefully we know that. Hopefully we've seen that a lot of times in pre-calculus, which is a requirement for this class. If you haven't seen that, let me know and I will send you some review videos. But we can do the same kind of thing with e functions. So I'm going to rewrite this as, do I bring this whole thing down to the other side of the quotient line? No. I only bring the base. That is the thing that the exponent is applying to. And here, the only thing this exponent is applying to is the e. If it was also applying to this -5, it would look like this, which it is not. So this is your base, the e. So when we convert it, it's going to look like this. -5 over e to the positive x. So now we have a e to the x, which we know how to find the derivative of. So now we're, at this point, we're forced to use the quotient rule, whereas if we knew the chain rule, that would have been a super easy one. So now we have to use this kind of crazy long quotient rule, but don't worry, soon we'll get the chain rule. So the quotient rule says we take, I'm gonna do the shorthand version of it. So I'm going to do the bottom times the derivative of the top minus top times the derivative of the bottom, and I apologize for my family fighting in the background, all over the bottom squared. Alright, so this is the bottom function, that's the top function, this is the bottom function. Alright, so I've got all this stuff in here. Now, let's go ahead and identify everything. So my bottom function is equal to e to the x, and we know that e to the x is that nice function where it's the only one that the derivative of it is also the same. Alright, and the top function is -5, and the derivative of the top is 0. The derivative of any constant is 0. So that should be nice. That should cancel out at least that first term up there. Okay, just a second here. Okay, so then we're just going to go ahead and plug everything in here. So the bottom is e to the x times that 0, which will end up just zeroing out that term, minus the top, which is top function is -5, -5, and we go and put that just so I remember to distribute that negative sign, times the bottom, which is e to the x, e to the x, this, all over the bottom function squared. So e to the x squared. All right, so let's see what we get here. So we're going to end up getting the negatives will cancel out. So this will be a positive 5 e to the x all over, and this will end up being, well, I'll just leave it like this right now. I could write that as e to the 2x, because remember, when you take an exponent to an exponent, you just multiply them together. But I'm going to end up canceling one of them out anyway, so I'll just leave it as e to the x squared. All right, so one of those will cancel out with this one, and I will be left with, and I'll go ahead and bring this one back up to the top. So I will be ended up being left with 5 e to the negative x. And that should be my final answer there. All right. And let me go and erase this little side work there. As long as I didn't make any mistakes, which I don't think I did. All right. And once again, chain rule is basically, we just give you a little heads up, is you just take the derivative of the outer function, and then you take the derivative of the inner function, which the derivative of negative x is just -1. So it's really just multiplying this function by -1, which just turns it positive. So it would have been a lot quicker. All right. This last one here is 24 times the cube root of y squared. So whenever we're dealing with radicals and derivatives, one thing we always want to do is convert those radicals into exponential form. So we need to make sure that we know how to do that. So let's make sure that we do know how to do that. So if we have a radical in the form of something like this, where this is a, and then we have some variable to the b, we can rewrite that as x to what? B over a by dropping that radical, right? So make sure that you know how to convert back and forth. And we do that, we can take whatever the root here is, and we bring it down underneath the b, like here, and then we can drop the radical, and vice versa. We can take whatever value is under this b, put it back, and make it the root, put that the radical back. All right, so now that we know that, hopefully we know that, let's go ahead and use this to work number 3 here. So we can say 24, and using that, this becomes y to the 2/3, and now this is just simply a power rule problem. So I'm going to bring that 2/3 out. So this is 24. The constant out front just stays there. So the 2/3 comes out front, gets multiplied, and then we have y, and then we're going to subtract 1 from it. So 2/3 minus 1, just like we've been doing all these power rule problems. All right, so then this is going to become 48 over 3, right? 48 over 3y. And I can leave it just like that. Oh, no, I can't, because 48 over 3 is, what, 16? I'll do that in the next step. And then 2/3 minus 1 is negative 1/3. So like this. And then, so this is 16y to the negative 1/3. So that's negative 1/3, which is equal to 16 over y to the positive 1/3. We usually like to make our exponents positive, and this is how you would leave it right there. So this is usually how we would leave it in this class, just like that. Positive exponents, like that. All right, and so that simplified form and simplified form. All right, if you have any questions, let me know. Good luck on the quiz. Make sure you're kind of studying these types of problems. Make sure that you have the formulas written down and that you've done some examples. Make sure you've also looked at some examples on how to find like second and third derivatives. That's just keep finding the derivative over and over again. For example, if I was going to find the second derivative of number 2, you know, it would just revert right back to this derivative right here, right? Because, well, why don't you see if you can find that out for yourself? All right, so have a great rest of your week. Thanks. Bye.